Multivariable calculus, we're on section 13.4, second page of the notes, projectile motion. Again, the projectile motion graphs that we're going to be looking at, an object or a projectile is fired with an angle of elevation of alpha, and what we're going to see is what makes this so very different is, t is going to be time in this application, but t is a parameter. It's hidden on this graph. We're going to have a horizontal position x. We're going to have a vertical position y. So we'll have an initial velocity vector v naught. And by the way, you could begin to envision what that would look like. I'm going to draw a separate picture over here. Here's velocity vector v naught. There would be components. Of course, that velocity vector would make an angle of alpha with the x-axis. And you can see that our x position, you might remember from last year in BC, so much of what we did, really just working with SOHCAHTOA, was x was equal to r cosine theta, y was equal to r sine theta. That means that our x would be our r, which is, of course, the length of our initial velocity vector here, times the cosine of the angle, cosine of alpha, and our y component would be the length of vector v naught times the sine of alpha. We're going to come back to that later. But of course, right now, what you see from my first graph, it's really a position graph. You can see that, the object would be launched. You remember in science and math classes, I'm sure, hearing that an object will follow a parabolic path when it is thrown. So we're going to assume that air resistance is negligible. The only external force is gravity. And we're going to try to develop the position function r of t. More to the point, we're going to write it parametrically. And we're setting up the axes in this case, so the projectile is starting at the origin. You can see us doing that more or less. Gravity, just want to let you know, if we're in feet per second, in feet, that's negative 32 feet per second squared for the force of gravity. If we were in the metric system in meters, that's negative 9.8 meters per second squared. We've dealt with problems like this even in calc. But tell you what, let's take a look real quickly and just say that right now the only external force is gravity. It's going to be pulling downwards. So we're going to say G, which of course already is a negative value to indicate direction. It's either negative 9.8 meters per second squared or negative 32 feet per second squared. And what we'll really do is try to get our velocity vector with respect to t, of course. And we can see even right here with a of t, at any given time, that's the only force acting on the object. But of course, we're going to integrate this velocity vector a with respect to t. And what that's really going to do is we're going to be integrating right here with g, with vector vector j, pardon me. And that means we'll get gt times vector j as we take our antiderivative, plus a constant vector. So, of course, as we integrate, we're always going to be bringing up a constant. But a little note, if we let t equal 0, we would quickly see that that constant vector would be our velocity at time 0. And another way to call that is what we see up above. It's this thing. It's our initial velocity vector. So writing this out, v of t for any given time will have gt vector j, but our c now, we could actually say, look, it's vector v naught. And rest assured, vector v naught, we could even break into ij components. In fact, we'll do that in just a moment. But let's bring this back up here to the top as well. And we could say, well, what about r of t? We need to get our position vector. That's ultimately what we're aiming towards. Of course, what we're going to do is really just integrate right here, integrate our velocity vector with respect to time. So how is that going to look? Well, our velocity vector, we can just recopy it right here. It's gt times vector j plus vector v naught. And let's work this integral out. As we are going to, take our antiderivative here, we're going to bump our t up to the second power, and that means we're going to get g over 2 t squared vector j. And this will just be v naught times t, and then we've got to add to that some other constant vector d. Now, real quickly, if we let t equals 0, of course, we'd see that r prime of 0, or r of 0, I should say, we'd let the t squared and the t equals 0, that's what vector d is. But we're starting at the origin here. So that means that r prime of 0 is really just the vector 0, 0. That means vector d is 0, 0. And what does that really mean? It means that if we continue over here, we could say that our position vector r of t is g over 2 t squared j plus v naught t plus 0. Because d just goes away. Now this is correct. This is definitely going to be fine. But listen, v naught has two components to it. So if you go to this far left edge over here, you could see that v naught has an I and a j component to it. So we're going to go there right now. We're going to say, you know what? V naught is really going to be, if you think about it right here, I can put some brackets in. It's v naught, the length of v naught, times the cosine of alpha I plus the length of v naught sine of alpha j, and then we're going to say that's times t. And of course, if we were to just pull this all together, we're really painstakingly breaking this down. But we've got g over t, t squared j. If I distribute my t, I'm going to put the t right in between here. And this is going to be the cosine of our alpha. And then we'll have I. I'm going to distribute the t right in here, and we'll say plus the length of v naught t sine of alpha, and then we'll have vector j. Now, of course, we could then just say what's our position function in terms of parametrics. X of t is simply going to be the I component, and that's going to be right here. It's going to be the length of vector v naught times t times the cosine of alpha. This is the horizontal position at any given time. The J's, if you look at the J's, you'll see that we've got G over 2 T squared right here. That's your first part of J, plus the length of your velocity vector times T times the sine of alpha. And that's your Y component. So this right here, these are the typical formulas that you're going to see in a physics textbook when you're dealing with projectile motion. So with this in mind, we can now approach an application problem. And we can say, well, look, we know that X is going to be, V naught times T cosine of alpha. We know that Y of T is going to be G over 2, sorry, T squared plus, here's your length of vector V naught T sine of alpha. And let's just read this problem together. It says a projectile is fired with an initial speed. Guys, that speed is the length of the initial velocity vector. Wow, we've got that already. Angle of elevation, that's alpha. Position of 10, that's your initial starting Y value. Tell you what, we're going to just real quickly say, add in a 10 right in here. Obviously, if we plug in a 0 for our T, we want to be at 10. And what's going to happen is, without too much work, you're going to say, look, I've got 150 times T, and then I've got the cosine of 45 degrees. Right over here, I've got Y is going to equal, well, we're in meters, so we're going to have negative 9.8 divided by 2. That's negative 4.9 T squared. And my V naught is 150. And then I'm going to have the sine of 45 degrees plus 10. And wow, we can clean this up so fast. This is really root 2 over 2. And divide 150 by 2, and we'll get 75 root 2 times T. Clean this up right over here. Very similar work. And we're going to be able to get root 2 over 2. This is 75 root 2 T. And then we'll say plus 10. So, hey, look at that. We've got our two position components for X and for Y. They want to know where does the projectile hit the ground. You can imagine it's launched 10 feet up. What they're really saying is, what's that X position when it hits the ground? That means we've got to let Y equal 0 for this one. So set Y equals 0 and solve. And guys, this is where you want to solve on the TI-89. And you know what? We're running out of a little bit of time right now, so I'm going to pause the video to get this typed in. Pressed F2 to hit solve. And we've typed this all in, but tell you what, we've got to set this equal to 0. So F2, then you say comma with respect to T. We've done this before. In just an instant, you should get an answer. Wow, I'm having a little bit of trouble here. Argument may not be an expression. Hold on. Sorry guys, I had a little bit of a typo. I had a 0 after the parentheses. You should get 2 times 21.74 or negative 0.0938. Hit green diamond, approximate. So that's the T value that we're going to have when we're going to be able to know that we hit the ground, 21.74. If you want to know the position, you're going to have to plug that in for X. So it's going to be 75 root 2 times 21.74. It's that many feet where you're going to be hitting the ground. So we'll just get that typed in real fast. And hopefully we can finish the video with that. And a position of, well, hit green diamond, enter. 23